Hello everyone and welcome to this new video where we discuss mathematics and physics on the board. Today we are going to discuss very quickly something very simple but basically that we have not really addressed in any of the videos, and it's just to show one of the many ways to understand where this law, let's say, is coming from. Okay, and this has to do with hydrostatics. Okay, so let's put a little bit of context here. In this square, I'm representing like a fluid. So a fluid usually could represent anything from a gas to a liquid. Now, the word hydrostatics refers to hydro, so that's related to water. And often this is something, and especially the formula we are going to derive, that would be true in liquids. Not necessarily so, and I'm going to talk a little bit about this at the end of the derivation. Not necessarily in air or, let's say, lighter fluids, and then it's going to maybe depend on the distance we are talking about. Okay, so let's set the stage. So we've got a fluid, then we denote the mass density of that fluid, so per volume, per unit of volume, rho. That's a traditional kind of notation for it. Then in this fluid, we admit that there is also a pressure field, so that I call P. And I'm going to assume that this pressure actually is not going to matter anywhere for the derivation, but only depends on the Z coordinates. Okay, so along that particular direction. And then we also assume that we are on Earth and that there is some weight that is going to act on the fluid. Okay, so the way this diagram works is that you imagine that you are in a fluid, and then you imagine what you call a fluid particle. In fluid dynamics, that's what is called the Lagrangian viewpoint, whereby you imagine the fluid particles. Usually you represent it as a sort of cube or some sort of cuboid or something like this. Perhaps that can be also like a parallelepiped as well in 3 dimensions. But in any case here, this is a cube. And then you want to know what are the forces that are exerted on that piece of cube. Now, it's not like this is a real cube. It's just you imagine you've got a uniform kind of looking at this fluid, and then you virtually, cut within it a sort of cube, and you see what are the forces acting on it, as if there were actual walls there. That's kind of the way this particular model, this Lagrangian particle model, works. So essentially the way it's going to work is you have the pressure field is going to act on it. Now the pressure field is acting on the in the normal direction on a surface. Okay, that's by definition. So a pressure is acting normally to any surface. Now here what we see is that the pressure field can act that way, that way, that way, that way, and also in, front and back as well. But as I said, the pressure here is only going to vary in the Z direction here, and basically as a result, there is a balance of pressure in these directions and also at the front and from the back. Okay, so at the end of it, what you have is that if you want to list out the forces, you get the force due to pressure, and that's simply going to be equal to, so this is going in that direction from the top, so that's minus P of Z plus dz, and that's in the Z direction. And then plus, so that's from above, plus, and then P of Z, and then Z. But then I need also, because you know that the pressure is a force divided by an area, so I need to multiply both by the area. So if you are acting in the Z direction, you're actually acting on the area which is in dx dy. So here this is dx dy, and here dx dy as well. So you've got the actual pressure force here. Now there is a final force that we are going to talk about, which is weight. And then in that case, the weight that I can try to depict here by some arrow that goes from the center of mass of this fluid particle, and then W is equal to minus rho, then that's dx dy dz, and then in the z direction as well. So what we are going to see here is W is equal to minus rho, and then dx dy dz in the z direction. So this is a list of forces that I can catalog, if you will, and I'm assuming that there is no other forces that somehow I'm not seeing, etc. Okay. In particular, I'm assuming that I am at equilibrium. So this is hydrostatics. So what that means is that there is nothing moving there. So there is no dynamical forces or kinematic forces acting on the system here. Now, if I want then to apply very quickly the laws of Newton, then I'm going to say that I'm visualizing this from an inertial frame. That's really crucial to apply Newton's laws. And then what that entails is that I can use Newton's second law. Which is F is equal to ma, and here this is equal to 0. So dynamically, essentially, the system is at rest. And again, it's important to say that it's at rest dynamically, because you could be at 0 velocity, say, in one frame of reference at a particular instant. But obviously, if you have a non-zero acceleration, then you're not really at rest. Okay. So basically, that's what we write. So what that means, so that's the definition of hydrostatics. And then we are going to have minus P of Z plus dz plus P of Z is equal to, in fact, let's put everything here. So we are going to get minus rho dx dy dz, and I forgot here, I always forget dx. Let's actually put, let's do as if I had already put them, and so I forgot, by the way, I just see that I'm forgetting stuff. I forgot the g here. That's important. That's the acceleration of the weight on Earth. And so here we are going to get, so minus plus p and minus rho g dz is equal to 0. So what I do when I'm here is that I say that p of z plus dz is approximately equal to p of z plus dp dz dz. So that's a first order Taylor expansion. I've provided, like if you go back to some videos, I've provided a way to get a Taylor expansion in that fashion. And then we get minus rho g dz equals 0. So when I put, no, sorry, I'm going a bit too fast. This is p of z plus dz, and now I need to sub that into this equation, and I get minus p of z plus minus p of z minus dp dz dz plus p of z minus rho g dz equals 0. And this leads us to the following equation. dp dz is equal to minus rho g. Okay, so this equation is very important. It's called the hydrostatic equation. Or hydrostatics, or like equilibrium equation. Okay? Now, often what people do here is they say, let's assume that rho is uniform. That's a traditional thing that people are going to write. And then basically you can solve that very easily to get that P of Z is equal to minus rho and then G Z and then plus some constant here. Okay. Now there are some ways if you define your variable as being some altitude minus Z. If you do an altitude minus Z, then you actually get the depth that you're going from the surface. And so in that case, you're going to get plus rho g. So for example, one possibility would be to say that that would be the atmospheric pressure and then plus rho g. And then you can call that, let's say, call that d for depth. So that's a traditional equation that people would use if you want to know, if you have a swimming pool, for example, and you want to know what is the pressure at the bottom of the swimming pool, you would use this particular equation. The only thing I've done here is that I've said that C was determined when Z was basically Z equals 0, for example, if this is surface level of where you are, and then you go then deeper, so basically less than 0 after that. Okay, so depth here would be minus Z, if you will. So that's basically a possibility of getting there. And so this equation, this is usually called the hydrostatic law. And that works very well. Okay, so that's this one. That works very well in liquids. And again, if you want to see at the bottom of the sea, this would work quite okay as well. These things work very well. Now, basically, that's it for today. The only thing I'm going to mention here is that this particular, so this is fine, okay? What is less fine, and that you find everywhere, is this step where you imagine that rho is uniform and then you kind of integrate. The reason why this is a little bit conceptually weird is because it's inconsistent with thermodynamics. And the reason why is because in thermodynamics, you cannot, like zero, you cannot have an increase in pressure that is not commensurate with an increase in density. And that's part of a very important concept in thermodynamics that is called an equation of state. You need to have, if you maintain the temperatures the same and maintain all whatever other intensive variables the same, you need to increase the density to actually get a higher pressure. And this is not captured by this part of the derivation where we assume rho to be constant, essentially uniform across everything. Now, that doesn't mean that rho actually is not undergoing a tiny little change that somehow we don't take into account. That's exactly what happens. In fact, that's why it works. But there is nonetheless a conceptual issue in the way the derivation is presented. Okay, so I think this is conceptual issue or a sort of legitimate for kind of not misunderstanding, but let's say a happy accident that somehow we can do it in this particular fashion. And that's why here I'm just saying that essentially we are omitting the fact that in principle the pressure need to vary commensurately with the density. You can't, if density really doesn't change at all, you can't get any change in pressure. Okay, so that's kind of the bottom line that I wanted to put at the end, and in particular, these kind of things are going to matter when you look at this equation, but then in gases. And for example, in the atmosphere, and you want to see how the pressure varies with essentially the altitude, and in that case, you're going to find a completely different law compared to this one. Okay, so that's something that people need to be aware of. This step of the derivation is kind of a bit dodgy in a sense, conceptually speaking, at least. All right, so if you've got any questions or comments, by all means, do let me know in the comment section, and otherwise, see you in the next video.